Great. Hello, everyone. Your lab coming up is a synthesis lab. You'll be running a reaction with eugenol oil that you had collected using steam distillation, and you will be making eugenol benzoate. The synthesis experiment requires additional sections for your pre-lab notebook entry. You have this lab procedure available, but let me skip to the very last page because we want you to prepare well for the lab by filling out your pre-lab entry properly. Now, you should be familiar with a lot of the sections. Title, page, and date, for sure. Next comes a pictorial abstract. For the reaction, you should really put the chemical equation, and then underneath the product, you're going to give us the theoretical yield in grams. How much product would you expect if everything goes perfectly? And so I'll show you how to do that calculation. So anything in red is actually new. If there is any special glassware or technique that you're using, you could sketch it, or some people like to draw a little flow chart. Do I have that? Here, flow chart. And if there's a mechanism given, you should draw it. For this particular reaction, we are not giving you the mechanism, so you don't need to draw it. Next is the purpose. You really should have the chemical names in the purpose because you're going to react. Starting material A with starting material B in a I don't think we tell you what kind of reaction this is, but it's a what is this? This is it's called an acyl substitution. You don't have to write that because I don't think that's in the handout. To make eugenol benzoate. There is a reason though why you are making eugenol benzoate, so you can explain why. That's all in the handout. Okay, I'll leave it to you to read the handout to fill in the why of the experiment. Also, if there are any notable techniques or instruments you're using. All in the purpose. Next is the source of procedure. After the source of procedure, there are two new sections, the materials table and the stoichiometry table. And in this video, I'm going to show you how to do those calculations and how to fill it out properly. Basically, I am writing out the pre-lab for you, except for the things that you should do on your own. After that, you're going to have the procedure, and then after that, you have the observations. The location of the materials table and stoichiometry table, I want it to be in between the source of procedure and the step-by-step procedure that you will write out. Alright. So let's say we get up to let's do the pictorial abstract, okay? Because I want to show you where to put your theoretical yield and how I would do it so you don't forget. So here's the notebook. I'm on page 15. You will give me the title, okay, there, and you'll give me the date here, and then pictorial abstract. That's the reaction here, so you are drawing that. Okay, I'll draw it out because I want to show you where to put the theoretical yield. It doesn't have to be neat. Definitely don't erase mistakes, just cross it out. This is a eugenol clove oil that you isolated, hopefully. And then we're going to react it with what's called benzoyl chloride. Uh-oh. I might run out of space. I did run out of space. You're going to use KOH as a base. It is aqueous. And then I don't have enough room for my final product. That's fine. Just put it down here. We're really appending these two molecules together, we're going to lose some atoms. You're going to notice that we lost a chlorine. So there's no chlorine in the final product. And we lost this hydrogen. See how there's no hydrogen there on this oxygen anymore? And we append, what do we want to call this group? This, it's a benzene ring. It's a phenyl group. We made an, how about this? We made an ester. Okay, we made an ester. Okay, so hopefully you can rationalize that we take this molecule and this molecule, we put them together. Yes, we did kick out chlorine, and that chlorine hooks up with, whoops, okay, so don't black out, just cross it out once or twice. KCl, that H hooked up with this OH to make water. Okay, so what do I need? In red, I'm going to put a box here, and let's not use red. In green, you're going to calculate the theoretical yield and put it underneath your product. This will be in grams, and really it should be 3 significant figures. Okay, 3 significant figures. Most of our numbers are going to be 3 significant figures. Okay, so that's what I mean by this. People forget, and I take off a point if you forget to put your theoretical yield. Okay, next, materials table. So let's say you're cruising along, you drew some glassware, or you know, the technique we're using is that we're going to run the reaction in the test tube, and we're going to add stuff to the test tube and shake it, and then isolate it via partitioning between 2 different immiscible solvents. So, who knows? Maybe you want to draw a test tube and say, here, add these ingredients. Add starting material 1, and starting material 2, and some KOH into your test tube. So that's one kind of cartoon that I might consider drawing. We need to figure out this, okay, and we need to draw the materials table and the stoichiometry table. So this is how we're going to do this. Pretend that you already did your source of procedure. Okay, so pretend that you already did your purpose and your source of procedure. And now we are at the materials table. I like to give a notation to my starting material so I don't have to draw it all the time or name it all the time. And the way I give it a nickname, or I don't know what to call it, give it a notation, that's starting material 1 and put a squiggly line under it. Starting material 2, put a squiggly line under it. If you're typing this, normally you would make it in bold, but sometimes it's hard to tell what's bold and what's not when you're handwriting it. So I put a little tilde or a squiggly line. And we're going to describe those 2 materials. So here's 1, and here is 2. Okay. We also have KOH. KOH. So you're putting in the main materials that are in the reaction. Now later on we're going to use some other solvents to kind of purify it that typically doesn't go into the materials table. Let me double check if that's true. Actually we should, because we want to note the hazards. So in the procedure you'll read that you're also using ethyl acetate. Ethyl acetate is the solvent that we're going to use to help isolate it. So this is not the TLC solvent. This is not characterization. This is the chemicals you're using to make the product and to purify the product. And ethyl acetate is one of those solvents. Okay. What do I want here? I would like the molecular weights of the main ingredients, so 1 and 2. And I actually have that listed here, but sometimes you're going to have to Google it or look it up. The molecular weight is in grams per mole. Okay, so I like to put the molecular weight in the materials table. So number 1 is 164.20 grams per mole. Number 2 is 140.57 grams per mole. KOH, we don't need the molecular weight because we're using a solution that's already pre-made. That solution, let's see, if it has a concentration, I would put it down. See how it says 5% aqueous? Let's put that down. 5% aqueous. And ethyl acetate is the solvent. We don't really need to put the molecular weight. It's not important for us to know the molecular weight of this to get the theoretical yield. Okay, so the molecular weight is definitely for the starting material. The concentration for any solution you're using in the reaction. Now, what comes next is something that people tend to forget. In the same materials table, I'm going to put a box here because you're going to fill out the characterization. What does it look like? So for instance, this box is during lab. It's not pre-lab because you don't know. You don't know how these materials look like. So that's us during lab. You don't know if it's a white solid, a white powder, or a grayish, ashy, solid. We don't know. So when you get into lab and you start using these materials, you're going to put the characterization. So let me give you an example. You know, this looks like water, ethyl acetate. It's clear and colorless. I need both. Clear or transparent and colorless. If there's one mistake that people have for this pre-lab entry for this experiment is they forget to put this. They forget to fill in this box. Okay? Don't look it up on Google. You literally want to set your eyes on it in lab and describe exactly what you see. Okay? We do this because if there is a low yield or if the reaction doesn't work, we can always go back and say, well, you know, this was brown and normally when we buy it it's white, so maybe it degraded. So we want a physical characterization just in case we need to backtrack and say, well, something went wrong. Could it be possible of this discoloration? Now, if it's discolored and it still works, great, right? We're not going to waste it. We're going to use it. And so that's why, again, you want the characterization because in case it does work, you don't have to worry that it's brown if you want to rerun the reaction again. Okay. Still at the materials table. Okay, still. One, you're going to list the compounds again. And now you're going to Google. You're going to Google the hazards. So here, this is pre-lab now. Before lab, Google the hazards and list them now. This is before lab. This is during lab. Got it? Okay. What are we up to? That's good for the materials table, by the way. Now comes the calculation heavy part. The stoichiometry table. The stoichiometry table, it's by itself, looks pretty simple. Let me show you that. It's the calculations where it takes a little bit of time. You understand that all your observations and everything that you want me to see has to go on the right-hand side on the odd numbered page. So that page that we started on was 15. This is 17. Great. Our stoichiometry table is at the top. It doesn't have to be. Stoichiometry table. You are only putting the main molecules that end up in your final product. What do I mean by that? This is your final product, okay? And so most of these atoms, actually all of these atoms, came from these two molecules. So we only need these two molecules in the stoichiometry table because these are the molecules that are important to figure out the theoretical yield. I would also like you to put the product in the stoichiometry table. What are we not putting? We're not putting that. Okay, that's not a catalyst, but it helps the reaction proceed. We're not going to put ethyl acetate because that was, in the procedure, that was part of the purification. So in the stoichiometry table, literally it's the molecules that you need to figure out the stoichiometry. Right? What's stoichiometry? It's the numbers that help you determine stuff like percent yield and the molar ratio and the theoretical yield. So you're going to skip 2 lines. 1, 2, product. The first column is going to be amount. That's not the molecular weight, right? The amount is how much did you literally use. And so, let's see if I can find that real quick. So it will be a number that you have to predict because this is the part of the prelab. So I know it says here 0.50 to 0.55 grams. But for us to figure out the theoretical yield, we have to pick a number. Okay, so I want this to be filled out before you come into lab. So let's say we're going to choose 0.50. I think we really should use 3 significant figures. So add another 0 and put grams. When you do the actual lab, and let's say you use a little bit more, right? That will be in your observations. So let me just put a check mark. We'll finish the stoichiometry table, or we'll do most of it together, and then you're going to put the procedure, right? And then you have observations. So let's say you don't use this. Just write in your observations. Say, used 0.510 grams. Okay? And that way, yes, you could recalculate later, but we really need to do the calculations before lab so we get a sense of how much product we expect. And so that's based on this number here. I just chose this one. Okay. So that's the amount. Take a look at the, this one's a little bit tricky. The second starter material is a liquid, and it says here, there, 12 drops. But I'm telling you 12 drops is that many milliliters. So go ahead and do the calculations. 12 times 0.050 milliliters. 0.6. So I'm going to put here 0.600 milliliters. But I want to convert that into grams because I want to convert the grams into moles eventually. So we need the density. The density is, I have it listed, but you may have to Google it, is 1.21 grams. And so how do you get, grams per milliliter. So look at this calculation. 0.600 milliliters times 1.21 grams per milliliter, and you cancel out. Okay? Times 1.21. So my gram amount is that, 0.726. 0.726 grams. I'm trying to save space because we need 2 more columns actually. You don't have to put a line, but I'll put a line here. The product amount is going to be your theoretical yield in grams, which we haven't calculated yet. Now the next column is moles. Okay, and so how do you figure out moles? Well, we have molecular weight, right here. Oops, right here. And do you see how if we take that number, well, let's figure it out. We want moles on top. So it's for usual, right? So 0.500 grams times, I want moles on top, grams on the bottom. So the molecular weight is 164.20 grams per mole. So we'll put a 1 up here and put the 164.2 down there. You see how we get moles in that case? Because these two cancel out now. So let's do that calculation. 0.5 divided by 164.2. Oh boy. I do want 3 significant figures. Okay, so you could do scientific notation. If you don't like scientific notation, we could just copy exactly what we see. 0.0030, you round up when it's a 5. It's already moles, so you don't have to put the units. That is the moles. Understood? I really hope I'm doing the calculation correct. If I am, then you're just copying this, okay? But I want you to know the process because maybe in the post-lab or your final exam, you will have to do this from scratch. All right, so number 2. We needed the grams. We got it from the density and the volume. And the molecular weight here is 140.57. What was the math? Amount divided by molecular weight. Okay. 0.726 divided by 140.57. Okay. 0.00516. Let me pause. I just want to make. I'm trying to remember if this was reasonable. For you, just be careful with the numbers and what it is. Okay, don't try to overthink it. I'm not going to overthink it. I think that's real. Now the moles. I don't know what moles to put for the product because I don't yet know the limiting reagent. Okay, that will be a calculation that we'll do together in just a bit. The next column is called equivalence, and I'll just put EQ. EQ is the ratio, the molar ratio, but the issue is I want one of these to be the limiting reagent. You're going to set the limiting reagent compound to 1.00 equivalents. So I don't know the limiting reagent yet, but I'm going to put a little note here for myself. Here. Okay, obviously you're not going to do this. This is just taking notes so you know how to do this. Make the limiting reagent equal to 1.00 equivalents. And then based on that, figure out what the other equivalence is. So for instance, if this is a limiting reagent, okay, and we'll explain later what that means. But if this is a limiting reagent, this will be 1.00, and this will be x, and you solve for x. It's literally this divided by this equals 1 divided by x. Now, if number 2 is the limiting reagent, I want this to be 1.00, and then this is x, and you solve for x. This over this equals x over 1.00. Literally, it's the ratio, the molar ratio, but you have to figure out who is 1.00. We've gotten as far as we can without figuring out the limiting reagent. We haven't figured out this yet, and we need to because we need to put it, you know where to put it, underneath the product. So now I'm going to show you the calculations to figure out who is the limiting reagent. These calculations I don't need to see. But if you are wrong, I may ask you, how did you get that number? So I'm going to put it on the left side of the notebook. Okay, so I can reference it the student can reference it. But again, I am not checking for your calculations, so it doesn't have to be on the right-hand side. Okay? I will ask if you could reproduce that number if it's wrong. This number if it's wrong. Okay. Let me spell it out. What is the limiting reagent? It is a starting material that if I use it all up will give me the less amount of product. Because what that means is that when these two react, one of them is going to run out first and then the reaction stops. That is limiting the amount you get. That's why it's called the limiting reagent or limiting reactant. And so my first question is, what if 1 is LR? Okay, this is how I want you to do it. You might know some shortcuts, but the problem is when we get to more complicated reactions where we don't have a 1-to-1 ratio, then people get a little bit confused if they're not doing it systematically like I'm showing you. So for number 1, I have start out with 0.500 grams of 1 times. I need to get to the moles. So we did this calculation before. We're just redoing it. So 1 mole, and what was the grams again? 164.20 times. At this point, we will cancel out grams, and we have mole of 1. So we need what's called the mole bridge. Because for every mole of 1, I get 1 mole of product. For every mole of 1. Do you see how it cancels out? That goes away because that cancels. This goes away because that cancels. And then whatever number I have is now moles of product. What do I need? I need grams of product. Right? I need grams of product. Also, I need to know who is the limiting reagent. So we're going to multiply by the molecular weight of the product, 268.31. How do I know we're going to multiply? Because I want grams on top. 268.31 grams per mole. Do you see if I have grams on top, this mole cancels out. Okay, I'm running out of space, equals. When I calculate these numbers together, I'm going to get a number that represents grams of product. Do you see how everything cancels out except those two things? Perfect. So how do I do this fairly quickly? 0.500 divided by 164.2 equals times 1 over 1, so that's 1, equals times 268.31 times 268.31. Okay, I think that's reasonable. And so I gotta write it down here. 0.817 grams expected product if 1 is LR. So that number potentially will have to go here. I just have to figure out the other option. What if number 2 is the limiting reactant? What if this is the limiting reactant? Now this calculation is a little bit longer. Do you know why? What if 2 is LR? It's a little bit longer because I would have started with the volume. But since we already have the grams, let me start there. Okay, so we get this a little bit faster. 0.726 grams. I know what a lot of you are thinking right now. I think a lot of you are saying, hey, we already figured out moles of 2. that was used. Can we start there? Yes, you can start there. I choose not to. I usually like to start with the amounts. But yeah, technically, you are figuring out moles of 2 anyway. But I want to do this again from scratch. 140.57 grams. Okay. Look what cancels out. Grams and grams. Yeah, moles of 2. Oh, let me just label this, by the way. I know this is 1/1. Okay, and you might think, oh, that's not a big deal. Why do we have to even write it? Because I need to cancel out the compound 1 and replace it with the product. So it's kind of keeping me honest, so I know who's on top and who's on the bottom. This is called the mole bridge. I think of it as an old bridge because it bridges